So far, we have studied the titration curves of strong acids with strong bases. But what we are going to do now is to consider some experimental problems that may help us understand why titration curves are so important. In this case, we will start talking about something called indicators. An indicator is a substance that you add during a titration process. So again, remember that at titration you have the Erlenmeyer flask at the bottom and you have the burette, in which if you have an acid down here, you have a base down here, and you'll have a shape like this one shown in this picture. However, how do you know when you are at the equivalence point? Titration curves are useful because it helps you determine unknown concentrations here, because there is such a drastic change of pH that when you have a drastic change of pH, it means that you have reached the equivalence point. That is, you have added as many hydroxides than hydroniums there were at the beginning. Therefore, the amount of hydroxide that you have added will help you determine the concentration that is unknown here. But experimentally there's a problem, which is, how do we know that we have reached the equivalence point? And to do that, we use indicators. Indicators is a substance that changes color when it changes the pH. In this case, for example, phenolphthalein is the one that probably you will use mostly in the lab, is a substance that changes when it goes from clear to fuchsia, and that is a very dramatic change of color, in which, in that case, it tells you that you have gone through a large change of pH. Why? So first of all, notice that we will just add few drops, just few drops in here, and few drops is enough to appreciate the change of color. And in this case, phenolphthalein, which is the most famous one, you can see how when at low pHs, you have a completely different structure. You will see that the resonance is somewhat different, the bonding is different, therefore it absorbs a different set of wavelengths, and therefore this is why it changes the color. And so, for example, this is what a solution of phenolphthalein looks at pH 2, and this is what a solution of phenolphthalein looks at pH 10. So this is why it's important to use a little bit, to put a little bit of phenolphthalein in the Erlenmeyer during a titration, so that once you appreciate the change of color, that's when you have to stop adding, because, and then you record this volume, because that will help you determine the unknown concentration of the acid. Let's practice and let's give you an example of how we can use indicators and titration to determine unknown variables. In this case, it's an unknown monoprotic acid, so we need to know the molecular weight, or the atomic, the molecular mass or molecular weight. So you have an unknown monoprotic acid that you need to know its identity. A way to figure out is calculating its molecular mass. Okay, so you weigh this many grams and dissolve them in 50 milliliters, and then when you titrate the unknown acid, let's put it HA, we don't know how much it is, but when you add sodium hydroxide, it takes 25 milliliters in the burette to appreciate the change of color due to the phenolphthalein to reach the equivalence point. Okay, so this means that in 25 milliliters 2 molar, there is as many moles of hydroxide than acid. Okay, so can we calculate how many moles we had? Well, if we have 25 milliliters, we use 25 milliliters of sodium hydroxide. The concentration was that in 1 liter, or 1,000 milliliters, we had 2 moles of hydroxide, and of course 1 mole of hydroxide reacts with one of the mysterious unknown acid. This will give us the known the number of moles of acid. Let's do this fast. This is 50 divided by 1,000. This is 50 divided by 1,000, 5 times 10 to the negative 2 moles. Okay, and these many moles were in this mass. Remember that the definition of the molecular mass is number of grams per mole. Therefore, the molecular mass definition, mass is 122 divided by 5 point times, this is grams, this is moles. Let's see. Let me go to my calculator and let me calculate. So let me 1.22 divided by 0.5. I'm not sure. Yeah, well, this is 0.4 grams per mole. This is definitely a very low. I wonder if there's a problem with the numbers, but this is in general how you would calculate the molecular mass of an unknown. Of course, you go to the tables and see what acid would have this molecular mass because it's very specific of that molecule, and therefore you could identify the identity of the acid.